Welcome to this session of our lecture series on superconducting resonators. This series is brought to you by the NYU Nanolab, the Laboratory for Quantum Materials and Devices. We would also like to give special thanks to the NordTech Hub and the Microelectronics Commons for making this lecture series possible. In our previous session, we explored the coplanar waveguide or SCPW geometry, a member of the planar transmission line family, and we looked at different resonator implementations using this geometry. In this session, we will extend the same geometry to create superconducting CPW resonators. These resonators are a key building block in superconducting quantum circuits, such as those used in superconducting quantum computing, as well as in other interesting applications. We have three main learning objectives for this session. First, to identify the key difference between a standard CPW and a superconducting CPW, or SCPW. Second, to understand the reasoning behind the typical operating temperatures of SCPW resonators in superconducting quantum circuits. Third, to be introduced to the potential observable effects of kinetic inductance in these resonators. A superconducting coplanar waveguide, or SCPW, uses the same geometry we studied in the last session. The key difference is that both the center conductor and the ground planes are made of a superconductor, an element with zero electrical resistance that also expels magnetic fields. As a result, conductor loss in an SCPW resonator becomes negligible. Let us take a moment to understand the significance of this fact. To see why this matters, let's first examine the impact of scaling the lateral dimensions of a CPW. As we learned in the previous session, one advantage of the CPW geometry is that we can shrink or expand the width of the center conductor in gaps without changing the characteristic impedance, Z0. This makes the geometry very versatile. The trade-off, however, is that resistance increases as the conductor width decreases. Since resistance is inversely proportional to the cross-sectional area, reducing the width while keeping the thickness constant increases the resistance. In other words, scaling down a CPW increases conductor loss in the center path. You may be wondering, how important is conductor loss for the performance of a CPW? After all, as we discussed in previous sessions, resonators have multiple loss mechanisms, all represented in our lumped models by the resistance R. The answer depends on the application and the circuit size. So let's review this more carefully in the context of a quantum circuit. To simplify, we will focus only on internal losses. We will group all internal loss mechanisms together under others, except for the conductor loss. In this case, the internal quality factor, Qi, of the resonator is given by the parallel sum of Qcond and Qother. Let us now briefly derive the expression for Qcond, using the series RLC resonator for simplicity, though it can also be obtained for the parallel model. Qcond is defined as the total energy stored in the resonator divided by the power dissipated in the conductor. The stored energy is given by Wm max, the maximum energy in the inductor, which corresponds to the current at its peak. The power dissipated in the resistor is the square of the RMS current times the conductor resistance. Since the current in the resonator is sinusoidal, the RMS value equals the peak current divided by the square root of 2. Substituting this into the expression, we find that Qcond reduces to omega naught times L divided by R. Finally, replacing omega naught with 1 over the square root of LC, we see that Qcond is equal to the characteristic impedance divided by R. Armed with our expression for Qcond, let's now apply it to a practical example of a CPW resonator with dimensions commonly used in quantum circuit development, and see how significant the effect really is. For simplicity, we'll again use the series RLC model. Suppose our target Qi for this application is on the order of 1 million or higher, which is typical in quantum circuits. To estimate the resistance of the center conductor, we first need the resistivity of the material. In this case, let's choose niobium, a commonly used metal. The plot here shows the resistivity of niobium as a function of temperature from 0 to 300 Kelvin. As expected for a metal, resistivity decreases with temperature. Niobium is also a superconductor, so as shown in the inset, below its critical temperature Tc, its resistivity abruptly drops to 0 as the material transitions to the superconducting state. For this example, however, we'll treat niobium as a normal conductor. Let's assume our resonator operates at 10 Kelvin, where niobium reaches its lowest resistivity just before transitioning. Under those conditions, the resistance of the center conductor comes out to about 1.6 kiloohms. In calculating QCond, we should use the effective resistance to account for the actual dissipation in the current distribution of the resonant mode. For a rough estimate, R effective can be taken as half of the total DC resistance for the fundamental mode in a half-wavelength resonator, so we set R effective to 800 ohms. This gives QCond a value of approximately 6.25 times 10 to the minus 3. Using this value in the parallel sum to calculate QI, we quickly see that QCond dominates, making it impossible to reach the targeted QI. Furthermore, the current in the SCPW returns through the ground planes. Even though their cross-section is much larger than the center conductor, they still contribute some conductor dissipation, further reducing QCond. Therefore, achieving a QI of 1 million or more seems impossible for a resonator of this size and material. What if we used a different conductor? While better conductors could improve QCond, they still would not come close to the target. To reach this level of internal quality factor at these dimensions, a superconductor is required, because in a superconductor, QCond is effectively eliminated from the internal quality factor equation. Achieving QI values of 1 million or higher also requires minimizing other internal loss mechanisms, which remains an active area of research. However, using a superconductor is essential to reaching these high QI values. In addition to a high internal quality factor, a resonator must meet another key requirement to be used in a superconducting quantum circuit. For those unfamiliar with these circuits, this simplified diagram shows a basic configuration: a superconducting resonator coupled to a superconducting qubit. In such circuits, resonators are used to drive the qubit, read its state, link qubits, and more. To function effectively in a superconducting quantum circuit, resonators must meet two basic requirements. First, a high QI at the micron scale, and second, the energy in the resonator must be quantized. From previous slides, we know that a high QI at the micron scale is achievable with an SCPW. To understand the second requirement and how to meet it, we first need to revisit our discussion from the first session on energy in a classical LC resonator. Let's start with the simple LC resonator, initially without any energy. A cartoon representation of the energy in the resonator is shown on the right. Now, imagine that we provide energy to the resonator without specifying exactly how, since there are many ways to do so. As we learned, a dissipationless LC resonator will preserve this energy indefinitely in the form of periodic voltage and current, effectively behaving as a simple harmonic oscillator. Now we take the peak-to-peak amplitude of the current and place it on the x-axis of a Cartesian graph showing energy versus current. We then plot Wm, the energy stored in the inductor, represented by the blue parabola. At the ends of the red arrows, which indicate the peak current values, the energy in the inductor reaches its maximum, corresponding to the total energy in the resonator. When the current is zero, at the center of the plot, the energy in the inductor is zero, meaning all the energy is stored in the capacitor. The parabola of the inductor energy effectively splits the total resonator energy between the inductor and capacitor at any given current. For example, at a specific current value, the energy in the inductor is shown by the blue bar, and the energy in the capacitor by the purple bar. Together, they sum to the total energy. This relationship holds for all current values, including the extremes where all energy is in a single component. We have just examined the energy dynamics inside a classical LC resonator. Now, let's distinguish between continuous and quantized energy in a resonator. We must clarify that a detailed treatment of energy quantization is beyond the scope of this lecture. Our aim here is simply to introduce the concept in a clear and accessible way, to raise the learner's awareness of its importance in the context of superconducting resonators. Continuous energy means the LC oscillator can hold any value of energy. In the diagram, 4 arbitrary energy values are shown. The green dots represent the infinitely many energy levels the resonator could occupy, and the internal energy distribution between the inductor and capacitor changes continuously with the total energy. In contrast, quantized energy means the resonator can only occupy specific, equally spaced energy levels. It can jump between these levels but cannot exist in between. For example, if the resonator is at level 1, and we supply only half the energy needed to reach level 2, it remains at level 1. From a classical mechanics perspective, this may seem unusual, but it is fundamental in quantum mechanics. Notice that at each energy level, the oscillation of energy between the capacitor and inductor continues at the resonator's natural frequency, but is always within the boundaries of that level. When a resonator behaves this way, we call it a quantum LC resonator. Finally, the lowest allowed energy level, labeled 0 in our diagrams, is called the ground state, while the higher levels are referred to as excited states. This illustrates the second requirement for a resonator to be used in a superconducting quantum circuit. The question is, how do we satisfy this requirement? What must we do to the resonator? The answer is to suppress thermal energy so that the resonator reaches its quantum mechanical ground state, making the discrete energy levels observable. Let us explore this further by examining a criterion for defining the operational frequency range of a resonator in applications where quantized energy is required. To keep the resonator in its quantum mechanical ground state, the first criterion is that the product of Planck's constant, h, and the resonant frequency, f0, must be greater than 5 times kB times T, where kB is Boltzmann's constant, and T is the temperature in Kelvin. Under this condition, there's insufficient thermal energy to excite the resonator significantly, and it remains in its ground state. If we simplify this equation, we notice that this means the resonator's frequency must exceed approximately 100 times 10 to the 9 times the operational temperature in Kelvin. For example, to quantize a resonator operating at 1 Kelvin, the resonant frequency should be on the order of 100 GHz. However, there is an upper limit. The product of Planck's constant and the resonant frequency must remain below the superconducting gap, otherwise superconductivity could break down, which, as we saw earlier, is essential to suppress conduction loss. Another upper limit criterion is that the resonant frequency must stay below the plasma frequency of the material, which is generally satisfied if the superconducting gap criterion is met. Given these constraints, the common practice is to cool superconducting quantum resonators to millikelvin temperatures. Typical dilution refrigerators operate around 20 to 40 millikelvin, so resonance frequencies above 2 or 4 GHz are usually targeted for quantum SCPW resonators. These considerations place these resonators firmly in the microwave domain. Using SCPW and cooling them down fulfill these two basic requirements to use them is superconducting quantum circuits. Before concluding this session, it is worth mentioning kinetic inductance in SCPW resonators. As in the case of energy quantization, here we also must clarify that a complete discussion of kinetic inductance is outside the scope of this lecture. Here, our purpose is to present the concept in a straightforward way that underscore its relevance in the context of superconducting resonators. Inductance, L, which measures a conductor's tendency to oppose changes in current, has two components: magnetic inductance, Lm, and kinetic inductance, Lk. Magnetic inductance arises from the back electromotive force induced by the magnetic field created when current changes in the conductor. Kinetic inductance, on the other hand, is due to the inertial mass of charge carriers and an alternating electric field. In normal conductors and typical applications, magnetic inductance dominates, but in certain cases, particularly in superconductors and thin films, kinetic inductance can become the dominant contribution. We can see an example of the effect kinetic inductance when it becomes comparable to magnetic inductance in a 1994 study on niobium nitride superconducting coplanar waveguide resonators. In that work, the authors derived an expression for Lk showing that kinetic inductance is proportional to the magnetic penetration depth, lambda. Since lambda depends on temperature, Lk also varies with temperature, while the variation of Lm with temperature is negligible. Because Lk was comparable to Lm, the resonant frequency of their resonators changed with temperature, as illustrated in this graph for different film thicknesses. Let's review what we have learned. First, superconducting coplanar waveguide resonators are essentially CPW resonators in which the center conductor and ground planes are superconducting. Second, their main advantage is the suppression of conductor loss, which allows them to achieve high QI, a necessary condition for superconducting quantum circuit applications. Third, we saw that another requirement is for the SCPW to be in its quantum mechanical ground state, typically achieved by cooling to temperatures around 20 millikelvin. Finally, we noted that kinetic inductance, usually hidden by its magnetic counterpart, can become significant in SCPW resonators, for example by making their resonant frequency temperature dependent. Thanks for watching, and see you in the next session.